This lesson is about magnetism. It should follow a unit on electric current, but so far all you've reviewed is static electricity. In other words, electric charges that aren't moving. But since we are running out of time in the year, I want to go ahead and skip to magnetism, since this is a phenomenon that you encounter in your daily life. And then next week, we'll go back and talk about electric current and maybe the connection to magnetism. Now, electricity and magnetism are very closely related phenomena. In fact, you can't have one without the other. This fact was first noticed by Hans Christian Ørsted in 1820, a Danish scientist 200 years ago. The discovery that he made was that magnets can exert forces on a current-carrying wire. Later, it was discovered that a current-carrying wire can exert forces on a magnet. In other words, they are totally related to one another and affect one another. And those discoveries have led to all our modern technology. So sometimes in your history class, your history teacher will tell you this was a turning point in world history, things like the invention of the steam engine. But there's been no bigger discovery than the connection between electricity and magnetism, because that led to all of our modern technology. Here's a little demonstration just to show you the connection between electricity and magnetism. What is on the stand, on a little black stand, is a compass needle, which is a magnet. And then around it is what looks like an aluminum wire, sort of a thick wire. And he's going to apply an electric current to it. So let's see if this will screencast properly. So he's going to turn a current on now and watch the magnet. It actually will move perpendicular to the wire. Turns the switch off. It goes back to its original north-south orientation. Turns the switch on, and it moves perpendicular to the current. So what is a magnet? What are its properties? Well, the first thing you have to know about magnets is that they're natural phenomenon that you can discover in nature. And they always have what we call two poles. So they'll have one pole that we designate as north and the other as south. And a law of magnets is that opposite poles attract, whereas like poles repel. So let's take a look at that. So magnets can exert a force on one another, and they can do this when they aren't even touching. So magnetism is an example of a force at a distance, sort of like gravity. But unlike gravity, magnetism has both an attraction and a repulsion. Gravity only attracts. So this, in some ways, is just like the static electricity that you just learned about, where like charges repel one another and unlike charges attract. In a similar sense, that's what happens to magnetic poles. So electric charges produce electrical forces, and they have sort of a force field around them. Well, magnets also have magnetic poles that produce a force field around them. Now, here's an example of an electromagnet being used in a junkyard to pick up metal and put it in the back of a dump truck. So which is stronger, the gravity attracting the metal to the earth, or the magnet attracting the metal upward? Well, obviously the magnet's stronger. Again, gravity is actually a very weak force in the universe. It's just that it has no counterpart. There is no anti-gravity. In spite of what you might see on science fiction movies, gravity always attracts, and that's why it can accumulate and work over very, very long distances. Magnetism and electricity, on the other hand, have opposites, and opposites will cancel each other out. So they only work over relatively short distances. Here's an example somewhat like you saw earlier with the magnetic needle on the stand. If you take a magnet and just hang it by a string and let it sit for a while, it will actually line up pointing in the northern or southern direction. Okay? What's actually happening is there is an invisible magnetic field in the Earth itself, around the Earth itself. The Earth itself acts like a giant magnet. And the small magnet that you have suspended and the large magnet that is the Earth attract one another. Opposites attract, so what we call the north pole of this magnet is actually more properly called a north-seeking pole. So the end that points northward, we call it the north end of a magnet, but it's actually the north-seeking end. In other words, it is actually, in a sense, it should be called the South Pole because it's attracted to the North Pole of the Earth. But it is what it is because this was discovered a long time before we knew about North Pole and South Pole in the Earth and that there was a magnetic activity in the Earth. So the North Pole points toward the North Pole of the Earth, but it's the North Magnetic Pole, not the North Geographic Pole. Those two things are not in the exact same spot. So we could call the south end of the pole here, the one that's designated as S, we could call that the south-seeking pole, but we usually just call them north and south for short. Well, in a similar way, you can make a compass. A compass is nothing more than a magnet that's on a little pole, and it's allowed to turn freely. As long as you don't knock it off of that little prop that it's on, it will line up with the north and south pole of the Earth, assuming no other large magnets are in the vicinity. Now, here's an interesting property of magnets. They all have a north and a south pole. There are no monopoles as far as we know. Every magnet has a north-seeking pole and a south-seeking pole. So it doesn't matter what shape it comes in, one part of the magnet will point toward the north if you hung it by a string, and the other end would point toward the south. Even the round magnet that you see in the center of your screen there has a north pole and a south pole. It could be one side versus the other side, or even more likely, the inner part, the inner circle will be one pole, and the outer edge will be the other pole. So magnetic poles do have some similarities to electric charges in that there are two. There's a positive charge and a negative charge. Well, there's a north pole and a south pole. Like poles repel, unlike poles attract in a similar fashion to electric charges. Unlike electric charges, you can't have a single pole. So you can have a single positive charge or a single negative charge in the sense that you can have a proton or an electron, but magnets don't come that way. You have to have both poles. How does that happen? Well, let's say we had a bar magnet, as it's called, one that you might be familiar with, just a piece of iron that has been magnetized and it's got a north pole and a south pole. If you break it in half, it actually becomes two magnets. The part that used to be the middle is now an end of a magnet, and the part that used to be the middle will become a south or a north pole, depending on what the other pole was. Even if you break those pieces in half, they will keep on becoming smaller and smaller magnets with north and south poles. In fact, you can go all the way down to 2 atoms. Now, when you break 2 atoms apart, you don't get magnetism anymore, and that suggests that the atoms themselves are responsible for magnetism in the way that they line up. So, does every magnet necessarily have a north and a south pole? Yes, as far as we know. It's sort of like a coin. It's got a head and a tail. You can't have one side without the other. Now, I mentioned before that there's a sort of a force field around a magnet. We can call it a magnetic field. It's invisible, but it extends out of the North Pole and goes toward the South Pole and actually makes a very big circle, part of which goes through the magnet itself. Here's a bar magnet, and small pieces of iron, we call them iron filings, have been sprinkled all around it. And this helps you visualize the invisible magnetic field. You can see how the little pieces of iron are lining up along a force field. You'll notice that the two ends of the magnet have more attraction than further away. That's an indication that the magnetic force is stronger as you get closer to the magnet, the bar here. But you'll see there's some lines that go between the North and South Pole in the magnet itself, or at least along the surface there. So the magnetic fields essentially either make a loop or they attempt to make a loop. You may not be able to complete it, but you can see that they're definitely trying to, even if you look at the top of the picture and the bottom of the picture, they're trying to curve around in a loop, even if it's broken. So magnetic field lines, these force fields, spread out from one pole, curve around, and return to the other pole, and then move through the magnet itself. You can also reveal this if you put two magnets close to one another. Here's a north pole and a south pole close to each other, some iron filings spread between them, and you can see that there is some sort of force field of attraction between the two because there's a large collection of iron filings pointed. They're so dense you can't even make out the individual lines. Whereas if you put the same poles, two norths or two souths close to each other, the iron filings all move away. This shows that like poles repel. So there's no filings between the magnets. That means the force fields have pushed away. So we generally designate it moves in a loop, but we generally designate the field lines as moving from the north to the south. And again, where you see field lines, or in this case, the magnetic filings closer together, that indicates a greater magnetic strength. If you put a series of compasses in the magnetic field, you can see the various orientations of the compass needle. So the compass needle is a magnet. You have a big blue and red bar magnet, and you can actually see the different directions that the compass needles are pointing. As they're close to the bar magnet, they point perpendicular, but when it gets far away, they point parallel, and it sort of traces out the path of the field lines. Now, the question is, where does this magnetic field come from? Why is there an invisible force field around a magnet? Well, remember earlier we established that there's some sort of connection between magnetism and electricity. So just as an electric charge is surrounded by an electric field, it turns out that a moving electric charge is surrounded by a magnetic field. So any charge in motion, any proton or electron that happens to be moving, will create a magnetic field around it. Here is, it looks kind of orange, but that is a wire, and it's going through a little plate onto which have been sprinkled some of those iron filings. And you can definitely see that the iron filings are tracing out a pattern around the wire. That means there's a magnetic field as the current is running through that wire. If you put compasses on there, just like the earlier picture, you could watch the needles deflect in a circular pattern around the wire. So what it shows is that as you have an electric current, let's say that it's moving from the top of the screen to the bottom of the screen in that orange wire, the magnetic field actually is perpendicular to that. So it makes a circle around it. So where's the motion of electric charges in a common bar magnet? Well, the magnet as a whole may be stationary, but it has atoms whose electrons are in constant motion. And this moving charge constitutes a tiny electric current, and every electric current produces an associated magnetic field. So electrons are constantly orbiting around the nucleus. Therefore, electrons are constantly producing a magnetic field around them. That would mean that everything, in a sense, is a magnet because everything's made of atoms that have electrons, and moving electrons create magnetism. So why doesn't everything act like a magnet? Well, remember that magnetism has opposites. So if you get a bunch of randomly moving electrons, they're creating randomly oriented magnetic fields, and they can cancel each other out. It turns out that it takes sort of a special set of properties only in certain materials where the magnetism can line up and add together rather than totally cancel out. So again, every electron can be thought of as spinning, and that means it's a moving electric charge. Even if it's not even orbiting, it would be spinning and creating these magnetic field lines around it. If you get a pair of electrons spinning in the same direction next to each other, they actually create parallel magnets that can add up and make a stronger magnetic field. You get a lot of those together, and that's what can make something like a bar magnet. Electrons spinning in opposite directions will work against each other and cancel each other out. So most substances are not magnets because of those various orientations of the electrons in the atoms. But there are some materials, natural materials such as iron and nickel and the element cobalt, have certain areas in the way that their atoms are aligned that allow the electrons to spin together to create stronger magnetic areas. So in iron, for example, there are 4 electrons whose spin is not canceled by the other spins of the other electrons, and those magnetic fields add together. So every iron atom essentially becomes a tiny little magnet. And from the iron atoms, you can create what's called a permanent magnet. If you take a permanent magnet and place it in, if you take something like iron that can become a permanent magnet and place it in a magnetic field for a time, then little pieces of the iron will line up with the magnetic field. You take it out of that magnetic field and it will remain magnetic. So what's actually happening is, if you could see the atomic level of the way iron is structured, you get to what's called magnetic domains. It's little clusters of atoms where all the atoms line up in the same direction, magnetically speaking. And whenever you get a lot of domains lined up in the same direction, the magnetic fields add together and it gets more and more overall magnetism. So these are very microscopic. You can't actually see them. But if they're all randomly oriented like a normal piece of iron you might dig out of the ground, but you leave it in a magnetic field for a while, then those domains can shift and move around. And when a lot of them start lining up in the same direction, then it becomes a permanent magnet. So any ordinary piece of iron can become a magnet if you put it in a strong magnetic field, even something like a nail. If you have a magnet at home and you have an iron nail and you just sort of move the nail along the magnet a few times, the nail itself will become a magnet. The nail at first has atoms which are randomly arranged, but if you move it in the magnetic field for a little while, those domains will all line up, the magnetism will add together. Now there will be some domains that point in the wrong direction, and so there'll be a little bit of cancellation. And the other thing you should know about permanent magnets is, because this does require an alignment of the domains, they have to be parallel to each other. If you drop the magnet, you can knock the magnetism out of it because you can randomize those directions again. So if you have a permanent magnet but you drop it a few times, it will demagnetize. All right. So permanent magnets can be made by simply placing pieces of iron or nickel or cobalt, which you probably don't have access to, but iron's pretty easy to come by. You just place it in a strong magnetic field. You can take like I said earlier, a nail and move it, just rub it on another magnet, and it will become magnetized itself. Now you have to do this in a particular way. You have to always move it in the same direction. So I wish I had a video of that, but I don't. But you have to, what's called here, stroke the nail along the magnet, or vice versa. Hold the nail and stroke it with the magnet, but you always have to do it in the same direction. Then those domains will line up parallel, and the nail will become a magnet. It's going to be weaker than the original magnet, but you could still do it. So the nail starts out like shown in the top of the screen here, randomly oriented magnetic domains, little crystal areas in the iron are all randomized. But if you stroke it or place it in a stronger magnetic field, then those domains can line up and it become a magnet itself. So anything that can hold magnetism itself is called a permanent magnet. And again, only certain materials have this property. So here's a think question. Iron filings, the little pieces of iron, are sprinkled on a paper that covers a magnet that is not initially magnetized. Why would they line up with the magnetic field of the magnet? It's because they have little domains, even though they're little pieces of iron. And so the little pieces of iron will align with any magnetic field that's stronger than them. So each of them acts like a tiny compass needle and swings parallel to the direction of the magnetic field. So that is enough for this particular slideshow. That's enough of a lesson for this week. There are some other assignments. Make sure you complete them and turn those in. Thank you very much.